In today's short video, let's solve Rosalind's Bioinformatics 5th challenge, computing GC content. The problem statement says the GC content of DNA strings is given by the percentage of symbols in the string that are C or G. For example, the GC content of this DNA string is 37.5. Note that the reverse complement of any DNA string has the same GC content. More information here. And this is sort of the FASTA format that's going to be given to us in a TXT file. It's important to keep that in mind. And given at most 10 DNA string in the FASTA format, return the highest GC content followed by the GC content of that string. Okay, so basically my understanding whenever I'm solving this problem is that you're given the sort of sample data set. Typically this sort of caret or greater than symbol followed by the Rosalind FASTA format, and then the DNA string is going to be given in a TXT file, and then it should output the sort of highest GC content or ratio, I would say. So in this case, for example, you would have 1, 2, and so forth, counting every C and G in that DNA string and then calculating that over the current length of the unique DNA string in the TXT file, and then just divide it, multiply by 100. And then if you feel free to expand this sort of drop down and have more information regarding this particular problem. The primary approach that was used to solve this particular problem is purely based on how I sort of treated the TXT file and how it's supposed to be read in my case. So for example, in this case, whenever I'm given a sample data set, such as this one, from Rosalind for this particular problem, what I did was I treated this entire sort of input as one complete string, right? Because it seems here there's going to be leading and trailing white spaces, right, in that sort of TXT file. So what I did, right, for example, let's say I set this variable called D and A string, right? And then what I would do is I would say that, including the greater than symbol, I would do Rosalind, greater than Rosalind, underscore 6404, keep going, and it should end at this point where it says AAT. And keep in mind, all right, this is all treated as one complete string. Now this is sort of where the important factor comes into play. Because it's treated as one complete string, what then needs to happen is that for every single greater than symbol, we need to make a function that sort of treats it as of a sort of point where it's going to say, okay, so in this case, the greater than symbol and anything after that, so which is in this case, Rosalind underscore 6404, and considering that in the original problem statement, there was that convention where the range values was Rosalind underscore 00, and it doesn't sort of become greater than 4 digits right here, followed by the underscore, then it would treat that as sort of the name for that particular unique DNA string. So in this case, this is just ignored. So Rosalind 604, right? Apologize for the handwriting, 60404. And then anything that follows that will then be treated as the sort of DNA string that's unique to that sort of particular DNA string name, right? So C, C, so forth, and then G, G, G. And then at some point, we're going to encounter another greater than symbol, so that's going to sort of reset again. And now, right, so it follows that same general pattern, even if we're giving however many length of DNA strings we're given. Right, so in this case, one thing to keep in mind that we're not only are we keeping track of the DNA string name and the complete DNA string sequence, but we're also sort of calculating the GC content or GC ratio, I would say. So in this case, we're keeping sort of a count, and then at the end, once we hit this point, then we're establishing that count and then storing it somewhere. So that's the important factor that comes into play. So we're actually going to be creating a dictionary in this case, which is going to store 3 different things, which is, for one, well, in this case, I'm just going to use this convention. This is not the right syntax, but for the sake of the example, we're going to have this sort of unique DNA string name, for example, Rosalind underscore dot dot dot. This is going to be the key. But then, because we have that key, we're actually going to sort of use or have two different sort of unique diff values, right? Which not only is going to hold the GC value, but we're going to hold the DNA string itself, or this DNA string sequence that is unique to that particular DNA key, right? And then towards the end, we're simply just going to output the max of the entire dictionary based on that GC value, and then sort of just referring to that. And that's how you solve this problem. The programming platform that is used to solve this particular problem is Replit, and the language is Python. But keep in mind, you can use any language, any platform, as long as you follow this sort of same output that was provided by Rosalind. So as mentioned before, we are going to sort of write a function and then pass in sort of specific parameters in place. But so first things first is we're going to take care of reading that file and then sort of treating it as one entire string, right? Instead of those leading and trailing white spaces. So I'm just going to say file equals to open, and this is the sort of convention to, reading and writing into a text file. Keep in mind, I'm not really sure what the txt naming convention is, so I'm just going to wait. And the next is we're simply just going to assign, depending on the contents of that txt file, we're just going to read that. And then the convention for sort of making it to where we're ignoring the trailing and leading white space is going to be this sort of strip method right here. And before we forget, okay. Then following after, we're actually going to have sort of 4 different parameters that we're going to pass into that function, which is the key, and as a key, and as a string, and then we're going to have the new DNA, another string, and then we're going to have the dictionary, and then we're going to establish that count, right? Which, again, we're going to keep resetting it whenever we sort of encounter that greater than symbol. And then what we're going to do is, before we write into these parameters into that function that we're going to be creating, we're simply just going to make sure we're going to be returning it appropriately into a given variable, as you see here now. So we're going to name our function with compute GC, and then we're going to pass in the key, new DNA, dictionary, and then we're going to pass in the count, right? So we're simply just going to write that up here. Then we'll just say def compute GC, T, new DNA, dictionary, count. That's pretty much it. Keep in mind, this is all sort of taken from sample input, sample output, and I'll explain the time, space, and complexity later on. So in this case, based on these specific parameters, we're simply just going to establish a for I in range loop that's going to iterate based on the number or the length of the DNA string, And then before we forget, let's make sure we return the entire dictionary, which is going to be held here, and then we're just going to simply output and apply that sort of max method, right? So again, since every time we visit a specific index of that DNA string, when we encounter a greater than symbol, we treat that as sort of a stopping point where we'll say, oh yeah, this is a new unique DNA string, right? And then so in this case, we're just going to say, we're going to assign the key equals to that DNA string, I plus 1, because we want to ignore that caret, or not caret, or the greater than symbol, and we're wanting to sort of get that stub string all the way up to the sort of 14th element after it, right? So in this case, for example, let's say I was 0, and I and 0 in this case is the greater than symbol. So everything after that, from Rosalind 64, Rosalind all the way up here is going to be the key, right? And then we're just going to simply say new DNA equals empty, and this is just whenever we're encountering another one, we're actually resetting the entire sort of variables in place. And then we're going to make sure for everything else that we're visiting in terms of the DNA string sequence, we're just going to make sure we're making sure that we're keeping track of whether or not it's actually part of the DNA string sequence. And then we're incrementing based on whether or not the actual index that's visited, it's either C and G, because this problem is looking for a C and G computation. Technically you can even change this to whether A and T in this case, no problem. You can just be interchangeable. Then now we're just going to say count plus equals to 1. And then before we move on, let's just see new DNA equals new DNA plus DNA string I. And then we're constantly appending it every time as we iterate through the entire length of the DNA string, in this case when we're reading from the txt file. And then now what we'll do is we'll just assign that specific key within the dictionary the value of two different things, which is going to be the GC count, right? And which is important to establish whether or not what's being returned. And then the DNA string, exactly. Okay, let's see. Everything looks good. And then before we forget, let's make sure that we're actually going to be outputting the specific value that is very important to this particular problem. Okay. Final val, and then print final val 0. Oh, bad. Okay, let's see. Okay, so now we're simply just going to try this out. We're going to treat in this case, we're going to just treat this. We're just going to temporarily remove this or comment it out, and just want to say DNA string equals this temporarily. Oh, 1 second. Alright, we're just going to hard code it. Let's just see if it works out. No problem. See, if you had a txt file of much greater length, it would take so much time to actually manually change such. So now let's see if it works out. And we should be expecting, oh, yeah, I forgot to add the quotation marks, as this is a DNA, or a string I mean. There we go, got it. Line 3. Oh, there you go. Yep, as expected, it's going 6.91, and it is rounded. And keep in mind that Rosalind does have a standard error, which is okay. Alright, after downloading the entire txt file, whenever you're attempting to submit the solution, what you want to do is, depending on what programming platform you use, you just simply want to sort of input or read the txt file. So in this case in Python, all I had to do was, based on the txt file, I just apply it here, and when I run it, it's going to return this sort of value right here, and then you're simply just going to submit that into Rosalind, and it should provide a successful solution. And then with this particular problem, it is important to, considering there are sort of two different values for a given key, you can actually just call the final value, in this case, I believe 0 and 1. This should also return the DNA sequence. Got it, here you go. And then the time complexity is going to be O(n), and then this is because we're writing a for I in range loop and we're iterating through the entire length of the DNA string. And then the space complexity is going to be O(n), and this is going to be sort of based on, I would say, the number of things that we stored inside the dictionary.